Minna, you're muted.
Hi, everyone, and good morning. Now I think you can hear me, right?
Yes, I
Yeah,
can.
okay. So good morning. Well, good morning, good afternoon, good evening, depending on where you are attending this webinar. And sorry for the delay. I had some technical issues as this was actually removed from Eleco LinkedIn accounts just 3 minutes before start. So my name is Minna Kreivin, and I'm hosting this webinar together with Elego as before as well. We got an idea to arrange this event or this presentation when Elego was attending in the ISL conference in Detroit in October. And our presentation was awarded as the best presentation or the best paper of the conference. And we thought that why not to share this with the rest of you as well. You may remember that we had 2 other webinars earlier this year. And the other one was about the sustainability, and the second one was about engineering. And they are still available in Elego YouTube and Elego LinkedIn. But this one is more about the pilot installation in Turku Airport and the results we measured from the field. And I'm not here alone. I'm here with Otto Vainio from Elego. Hi, Otto.
Hi, Minna.
How
See you
are
again.
you?
Good. Sun is
Uh,
shining in Finland. It's a rare thing nowadays.
And congratulations for being awarded as the best paper of the conference. I give you this kind of virtual applause here.
Thank you. That's quite a surprise.
So our main purpose today is to go through your talk and share it with everyone. But we could start with the short recap from this year's conference. I was not attending, unfortunately, but Otto, you were there. So what was your experience in general?
Oh, I had a wonderful time in Detroit this year. It's first of all, it was so nice to get around people, get to see so many like-minded people gather, discuss, and have all this sort of vibrant energy going on. I could sense that people were expecting or waiting, had been waiting for this kind of an opportunity for a long time. So really refreshing experience.
Yeah, I bet they have been waiting for it. And we all have been waiting for it. I hope I will be attending next year. Uh, do you remember, or was there any specific topic or main theme in the presentations during the conference?
Yeah,
No, the
well,
agenda.
aeronautical ground lighting. It's oh well, yes. To me, there were many wonderful presentations, but one of the key points or key sort of themes that I was very delighted to see was the in-hand, real-world experiences from the airfields, from the installations, the contractors there, the problems they face, the problems the airfields face, because that's the kind of knowledge and information that we, from the manufacturer's point of view, we don't get that. We don't get that directly. We have to get that from the airfield, from the people actually working there. As we see in the presentation, we have our there's sort of small chances to get to the airfield and do some measurements, but that's of course a very tiny fraction from all the what's going on in the airfield. So getting a window to what happens at the field, what the problems are, what needs to work there, how to make things. So that was a very welcome and very kind of how you say fulfilling experience to see all that.
Yeah, and extremely important information for us indeed.
Yes.
Isn't it that there was a 1 day mini expo, or one day there was a mini expo in the conference?
Yes, there was, and we were involved in it. We had a booth there, and unfortunately, I wasn't able to browse the expo per se. I couldn't actually visit any any other booth. I was alone there from Elego, and I had a busy expo all 4 hours of it, just standing in the booth and having. But I had such wonderful discussions with people with many people from the US and even from the Europe and the rest of the world, even some. Uh, Such a busy, nice time. So many discussions. It was really very, how you say, lively occasion.
Yeah. I bet. I have only one last question in my mind. Like, was there any question or any conversation that was kind of a takeaway from the event, or something that
Uh,
surprised you? Well,
was the takeaway that would come back to the interest of the airfields themselves, the end users of the product, and what in the end what matters, how it works in the field and how it solves the problems, or how it actually prevents the problems, how the AGL works in the background to provide the visual cues to the pilots to operate safely. So if everything works well, nothing drastic happens. It just works. The lights are on and everything works fine. It's only when problems arise when this kind of experience, how to develop the products and work towards products and solutions that actually solve the problems before they even begin to happen. This kind
okay.
of an experience. This was really something I enjoyed.
All right. Super. It sounds like it was a good conference for Eleco as
Very good.
well.
Very nice.
Yeah. So why not to move on to your presentation and talk? It's about sustainability in lighting equipment reuse. It's exactly the same topic that you gave in the conference. And as always, if you have any questions, you on the other side, if you have any questions or comments, you can comment to the comment section, and we will go through your questions after the presentation. I think I will share the presentation, and after that, the stage is yours, Otto. I remove myself here. Yes,
Uh,
go ahead.
Is the presentation on now, or is it because I can still see myself full screen?
Okay, that's a good point. I tried to share it, but for some reason, now.
Oh, this looks excellent. I'll just stop the cam to save some bandwidth. So, the presentation is more or less, the slides are exactly what was presented at the IES. I assume that the version we are going to talk about here will be a little bit shorter in time, a little bit compressed maybe. Um, this talk, some of you may remember, if you remember the webinar we gave earlier this year, that was more of a general going over the Elego solution in the whole solution in not that much detail to the actual technical solution. So this talk will be specifically about a single pilot installation that we have been running for 1.5 years now, in its full scale, and the measurements and the data and the background to this technical solution. So we'll dig in deeper into the technology here and explain how we and in a little bit more detail how we do things and why it works the way it works, and what problems it attempts to and solves. So if we go to the next slide, Mina will be in charge of the slide changes here again, and that's why I'll be asking for them every now and then. So the LED retrofit case. So the what we talk about, or the retrofit case here is really reusing the existing infrastructure as much as possible. So and then this is what our whole development was focusing on or based on. So and it's culminating in this is the first full installation uh, with this technology. So it's a CCR controlled LED. So the CCR directly controls the LED chip itself, which means that we can minimize the infrastructure changes in the field, minimize the amount of components in the field. We can reuse existing fixtures and existing cables, existing transformers, only replacing the CCR and an LED bulb inside the existing halogen fixture. And by doing this, by minimizing the infrastructure, it also, from that, follows that we can actually minimize the energy usage as well. So in this case, over 90% of energy changes were measured, and this talk will concentrate on how that is achieved, and finally show the details or show the results in more detail. So if we go to the next one, this is a brief sort of our categorization of the AGL technologies. This is by no means all encompassing or a general kind of a categorization for every situation. This is just how we look at our kind of view to the different technologies from our perspective. So there's of course the 6.6 amp halogen, which is perhaps the best known, the most far-reaching technology, using standard halogen currents to where the CCR directly controls the tungsten filament within the halogen. So that's a directly CCR controlled luminous output from a halogen fixture. A very robust, very simple technology. And when I talk about simple technology, I mean the simplicity as a good thing, where there's nothing extra brought into the field. So in that sense, it's kind of a minimized system. There's a 6.6 amp LED, which very nicely follows the halogen 6.6 amp standard, and the standardness of this technology is kind of a nice feature because it works well with the existing 6.6 amp infrastructure and 6.6 amp CCRs and all the bells and whistles built on top of the 6.6 amp standardization. But in this standard, the series circuit current, the current running in the primary and in the secondary, is not the same as the actual light producing component, the LED diode itself. And so there has to be some kind of a conversion. So there are technical reasons why this is not really feasible. That we'll go into more detail about that. So there has to be some kind of conversion. There has to be something brought in to make the conversion. Then an addition to that, or a slight variation of that, is the so-called information controlled LED. And this is sort of our categorization. There might be different ways of saying this, but we think that this name kind of covers the idea in a reasonably clear manner, so that there's the current of the primary and the secondary may not, or they are kind of detached from the actual light output. They can even be constant in some cases. So there's just a single current going to do something. The current amplitude is there just to provide the energy, but the actual luminous output from the fixture is controlled by information one way or the other brought to the fixture, so that the fixture knows what brightness level to choose, independent of the actual amplitude of the current in the primary, in the series circuit, primary and secondary. And then there's the technology that we utilize, what Eleko developed, this CCR controlled LED, where the CCR directly controls the luminous output of the LED diode, the actual chip in the component, the LED component, the diode. And this is very similar to the 6.6 amp halogen technology, where the CCR directly controls the luminous output without any active variations or control between the CCR and the LED itself, the diode. We control the LED directly from the CCR. So this is it's almost like the 6.6 amp halogen system, but the current levels are slightly different. And if we go to this next slide, that will be explained in a little bit more detail. The 6.6 amp halogen standard currents are between 2.8 and 6.6 amps, and this directly follows from the halogen technology. The tungsten filament needs to heat up to actually to very high temperature. It needs to start to glow to produce visible light. It starts producing IR before that, but to get to visible light, there needs to be a certain amount of energy spent already, and this 2.8 is the chosen standard value for that, where there's roughly 1% of light coming out from the. It's not that actually easy to control it that accurately at those levels, but this is the chosen standard current. But there's an offset, as you can see from the graphs on the right hand side. Between 0 and 2.8 amps, nothing really happens. The tungsten filament heats up, but it's not producing light. It's not producing visible light yet. Whereas the LED, it starts to produce light more or less as soon as there's any current flowing through it. A tiny bit of current going through the LED starts to produce a little bit of light. And the commercial LEDs nowadays, the nominal currents on the high current ones are up to 1 amp or 2 amp, 3 amp, depending slightly on the chosen technology, but it's still in almost any case in the simple components is far less than 6.6 amps, usually topping up at 2 point something or maybe 3 amps. The high power LEDs have been developing a lot in the latest years, and we've seen some variation and increases in the currents too there. But there's this fundamental difference of the halogen currents having an offset, whereas the LED starts directly from the 0. So a simple scaling with the transformer doesn't work. So what would scale the 2.8 to 0 would scale the 6.6 to almost 0 as well. So we need to shift the currents, not scale them. And by acknowledging this, we realize that we actually need a CCR that starts from the 0. So the CCR, if we want to control the LED directly, we need a CCR that will start from the 0. That will be able to run next to 0 amp currents in the AGL primary. And this is where the development started more than 5 years ago at Elego. So this project was more or less a research project in the beginning. So we really started from the basics, started from the scratch, seeing how we could make this work. On the next slide, there's a little bit more details about or just showing this same story about the halogen and LED differences. And this is actually the graph shows actual measurements from our lab from the very early days, where we started to look into these possibilities, how to actually control extremely low currents in a kilometers long AGL cabling in real environment. So with the LED, as said previously, 1% of luminous, or well, maybe I didn't say that, but I will now. The LED luminous output is more or less linear in its nominal range. Is more or less linear compared to the current, the mean current running through it. So if one wants to control dim the lights, as the AGL lights need to be dimmed because they need to be able to accommodate a huge variety of natural lighting, from clear dark nights to daylight fog. So a lot of light in the worst case scenario, or best case, depending on how you look at it, down to very, very small amounts of light in the clear night skies, where we don't want to blind the pilot. We want to avoid glare, even though the pilots are directly staring at the light source here, which is, by the way, more or less the definition of glare. But we want to avoid the glare effect. So the LED, this shows the same. The graph shows the same story, that the halogen, there's the gap again, but then there's a difference. The halogen current is also very much non-linear. the current to luminous output ratio. Whereas with the LED, it goes linearly. So if one wants to control the LED at for example, 1 or 3% of luminous output, the current also needs to go down to 1 or 3%, 10%, 30%, whatever the required luminous output level is. So the yellow, green, purple dots are measurements in an actual AGL circuit. This is in the laboratory, so the circuit is actually, it's not kilometers long, it's just a few meters or a few tens of meters. But this is a real AGL circuit still. So the LED is behind the transformer run by a CCR. So this just shows that the same fundamental principles of linear control work exactly in an AGL environment as they do in a normal LED circuit. So nothing surprising there. Just confirming the technology in an AGL setup. And then if you go to the next one, knowing what we needed, we realized that there needs to be improvements to the power delivery system. So this was then stepping back to the or relying on Elegos history on building and designing power electronic systems. So we knew that we needed a power electronic component capable of stably and reliably controlling small currents in an AGL environment. And we realized very soon that we need to understand the series circuit, the AGL topology, the chosen topology for AGL circuits in detail. In order to know what is required from the power supply, we needed to understand how the dynamics in a series circuit, in an AGL circuit work, because the series circuit, it's a very genius way of controlling accurate and even or what's the word? How even and stable control of power delivery through the lamp transformers in long range, and guaranteeing that because of the Kirchhoff's law, we know that the same current, if the circuit is intact, we know that the same current flows through the whole circuit, and when we are working in the operating rates of the transformers, the same current will also flow in the secondaries of the transformers, and this will provide the even power delivery. But the downside of this is that everything within the series circuit will affect the current. So if we want to understand how the series circuit works, we need to understand the entire circuit in its entirety. It cannot really be split into separate parts, or it can, but they all have to be taken into account in the total workings of it. So we built a detailed model of the whole circuit, a detailed power supply model, adjustable cable models, not quite the telegrapher's equation, but something similar. Accurate transformer models and detailed load models, meaning what happens in the fixture. Because we kept the parts in the fixture very simple, just putting, our aim was to control everything from the CCR, so we needed no active control electronics in the fixtures. We could actually build the load models into the same circuit model in a detailed manner. And we ran thousands of hours of computer simulations. The good thing about that is that you can just leave the computer running and do other stuff meanwhile. So that's the good thing about it. The bad thing is that it usually takes a few days, up to a week or two, to get the results. And you might then realize that something needs to be changed, and then you rerun them. And so it still takes a lot of time. But fortunately, other things can be done meanwhile, and working in the lab, for example. So what we learned from this simulation, in this next slide, there's a brief summary of what this computation taught us. It showed us that even though the 50-60 hertz sinusoidal current, the chosen 2.8 to 6.6 amps current, is a very it's field tested, of course, for tens of years. It's works fine for that current range. But we realized that for low current applications, if we want to go below 1 current, and if we want to go to the milliamp range, tens of milliamps in the lowest cases, the accuracy and the stability of the entire circuit can be improved if we step outside of this 50-60 hertz purely sinusoidal, single frequency sinusoidal signals. And we tested with a whole variation of different kinds of signals and frequencies. The tests were run with frequencies between 50 and 599 hertz, and even using modified waveforms, and show that there can be clear improvements with them as well. Sometimes beneficial, sometimes not really necessary. And this, by applying these changes, which are not exactly that big fundamentally, but make a huge difference in the operation of the entire circuit. We saw that a 6.6 amp cable and transformer circuit can be operated with just, in the lowest cases, it's just milliamps or a few tenths of milliamps, and it actually, the whole circuit is actually a very stable. It can be made a very stable and very robust circuit by handling the power supply in the correct manner. So the good thing about these long cables and transformers in there, that if that's taken into account in a correct manner, it actually improves the stability of the low currents and accurate control. Another feature, if we go to the next slide, is the lamp transformer fidelity, because it's not enough to run small currents in the AGL primary. We need to make the current or characteristic such that the transformers are capable of reproducing that current into the secondary, because that's, in the end, is what matters, what will be seen by the picture. This is, again, also fairly simple technology, technology-wise, or the fundamentals of this technology are quite simple. By modifying the waveforms, increasing the frequency even slightly, will have a huge benefit on the lamp transformer fidelity. So we can actually accurately reproduce the currents, the small currents in the secondary, if we slightly step outside of the 50-60 hertz signal. Higher currents would, of course, be run with the smaller frequencies. Smaller currents maybe with higher frequencies. Usually a compromise can be found where a single frequency even can be used, depending on the case and the waveform used. On the right-hand side here, you can see measurements from the lab with different frequencies on it. So this case example happens to be a 45-watt AGL lamp transformer, and we see that if we go lower with the current, so this is, the graph is showing the LED current divided by the primary current. So the fraction 1.0 would be ideal. But if we go lower with the current, this fraction starts to get lower and lower when the lamp transformer starts to lose its fidelity. But we can compensate that with slightly increasing the frequency and getting it back to an acceptable level again. If you lose a few percent here or there, doesn't really matter. The eye is not really capable of picking up a few percent of luminous differences. So this covers all the requirements of the series circuit itself. So knowing how we handle the primary, the lamp transformer, and the secondary current following that allows us to accurately control the current within the fixture from the CCR installed at the substation. So this is theory. This is lab measurements, computations, tests. and nothing that, or none of that actually matters if it doesn't work in the field, in a real operating environment where the primary cable is usually many kilometers long, and there are tens of fixtures installed behind secondaries that can be tens of meters each. Uh, we needed to go to the field, and that we did. On the next slide, this is a measurement from Helsinki Vantaa, actually, where we were very kindly allowed to run these test measurements. On the lower right hand side corner, you can see the layout of this exact measurement. There's the substation is where this orange dot is, where the CCR is, and the point of this measurement was to measure the current at three different places within the AGL circuit. So one was at where the orange dot is at the CCR, right in the beginning or end, which way you look at it, the series circuit. The blue curve or blue dot is the location of the first fixture. So where there's only the transfer lines between the CCR and the actual AGL installation, the fixture installation, and then the green curve is the middlemost fixture, so the furthest point electrically from the CCR. And we measured the current from the this was on the primary side, and also actually from the secondary side in this circuit. And on the graph, you can see the y-axis is milliamps. So we started in this case from roughly 3 amps, 3,000 milliamps. And so in this case, we varied a few of the parameters, but the x-axis actually shows frequency for this measurement. The frequency doesn't actually have to change, but in this case, we chose that as the axis or the parameter against which we check the operation. So in order to have an acceptable behavior in the field, we would need to have the same current measured at each of these locations, showing that we can deliver the current all the way in the same amplitude throughout the field, which would guarantee even lighting, so that each fixture would produce the same amount of light. And as you can see from the graphs, the three curves overlap more or less exactly all the way down to tens of milliamps levels. The lowest current we ran in this setup, which was measured from these places, was actually 14 milliamps. And with this current, the LEDs just showed a very, very tiny dim glow, but they were all on. They were all producing light. So that showed us that we can. That shows that there's in principle nothing against this technology of accurately controlling the LEDs in a reasonably. So this particular circuit is more or less 5 kilometers of primary circuit, and the 5 kV primary cable, 54 fixtures, happens to be a low intensity approach circuit. So knowing this, we knew that okay, there is a way to do it. A lot of details were at this stage when this was measured were still unclear, but we knew that we were on the right track. The technology in principle was working. And then if we go to the next slide, between that slide and this slide, a few hectic years of R&D, product development. At this point, we approached the level that we actually had a more or less finalized product solution already, still under development, still a lot of details to be fixed, but the fundamental technology and the operation and everything was also already in a field installable state. So Now we go to the Turku airfield upgrade installation. So this already, so as I mentioned in the beginning, this installation was the first full test installation producing or showing all the aspects of this kind of technology and how it can be how the LED can be brought into an existing halogen installation with minimal changes, minimal amount of new material brought into the field and minimal energy used. The installation was 58 taxiway fixtures and 9 guidance signs. Altogether in this circuit, there were 130 PK30V halogen bulbs with 45 watt nominal power. We changed the LED bulb, the halogen bulbs into LED bulbs. So because this technology allows us to minimize the components in the fixture, we could actually build the LED light source into the mechanical form following the PK30D, and there are actually reflector versions as well for the MR16 and MR11 sort of equivalent mechanically. So we, because the LED bulb follows the form factor of the PK30D halogen bulbs, we could use the existing still well operating fixtures just by taking the halogen bulb out and putting in the LED bulb. 130 LED bulbs with 6 watts of nominal power, and everything else in the cable signs, secondary transformers, circuits was reused. The CCR was the other component changed in the field. So the 6.6 amp CCR was replaced with this LEGO low current CCR. So on the next slide, we have a few more details of the circuit. So this one was roughly estimated 4.5 or 4 something kilometers, 6 square millimeter primary cable, 2.5 millimeter square millimeter secondary cables. 58 of the transformers were 45 watt EFLA, happened to be EFLA KR 551 type of transformers, and then there were 13 200 watts and 9 150 watt transformers for the guidance signs. So a fairly standard AGL installation, similar which can be found in many places. Nothing really special about this circuit as such. On the next slide, we can see a little bit more details of the actual installation. So this shows the halogen and the LED bulbs. So on the right hand side, there's this whitish bulb is the LED bulb, and on the right hand side, there's of course the familiar halogen bulb. So the halogen bulb has been taken out of the bulb, replaced with this LED bulb, and in this case, actually, there was a additional improvement made into the fixture, just making sure that the LED bulb sits tightly to the body of the bulb to get the heat out of the LED bulb, to increase the LED bulb lifetime. So, but this was, in this case, this was an optional improvement addition to the fixture, but we've seen that in many cases in these retrofit installations, it actually pays to put a little bit effort into improving the contact between the LED bulb and the body of the fixture, just to make sure that the heat gets distributed nicely into the body of the fixture, from where it can then dissipate into the environment. It's not needed with all fixtures. We have pilot installations where we didn't do any changes to the fixture. We just took the halogen bulb out and replaced it with an LED bulb. But especially for high intensity solutions where more power is used, it's beneficial to put a little bit effort into ensuring that the maximum lifetime of the LED bulb can be utilized. On the next slide, we'll see the same kind of inside view, or the same kind of how to, or behind the scenes, behind the panel from one of the guidance signs. In this case, actually, these are all LED bulbs already, but the first one on the right-hand side corner shows the improved fitting in here as well. So basically, we replaced the steel support for the bulb with an equivalent aluminum support. This was again to improve the thermal contact between the LED bulb and the body of the guidance sign. The support itself is mechanically similar. It's exactly replicating the dimensions of the previous steel support. It just provides better heat transfer. In this case, there would be also the reflector installed on top of this first bulb. It's just missing from this picture still. So the actual installation replicated the halogen installation one-to-one. So just replacing the halogen bulbs with LED bulbs and no other modifications other than, of course, this thermal improvement. But that was none of the geometry or none of the dimensions were changed, just the material from steel to aluminum. And after that, after we got everything working, in this case, it was visually the circuits and the currents were visually compared to the neighboring halogen circuits, making sure that the LED circuit didn't stand out one way or the other, so that it would work in conjunction with the other field, other taxiway circuits. And just as our theory and calculation showed, a 1.0 amp current more or less exactly replicated the brightest halogen bulbs in the neighboring circuits. The neighboring circuits were a little bit more uneven. The halogen bulbs don't give as the LED bulbs are a lot more steady and even in their output for a given current, even during aging. And but overall, with 1 amp in the circuit, we got more or less exactly the same response as from the neighboring halogen circuits with we're running with their nominal current or full power. So of course we needed to verify that with measurements. So visually everything was okay, but we wanted to know what happens in the circuit within the on the electrical side, which directly reflects to the actual luminous output in our case. So on the next slide, we will see, so this is a measurement, field measurement of the average current in the mid circuit. So this is, we took these measurements from various places again, but this is showing the mid circuit. So this is the furthest point from the CCR. So these are 5-second samples averaged over a single waveform of the AC side on the primary. But this measurement is from the secondary. So this is already after the transformer. So this is exactly the current the LED chip will see. So 1 amp, a little bit of jitter in there, but the maximum fluctuations are less than 1.2%. The same with 500 milliamps, half an amp, which would produce 50% of light. Curiously, though, we didn't take these measurements with these standard 1, 3, 10, 30% of luminosity. We had our kind of R&D hats on while doing this. We could have just as well taken them with the standard currents. For some reason we didn't, but doesn't actually matter. This would work exactly the same with the standard currents. The other currents were 200 milliamps, 100 milliamps, and 30 milliamps. And the same result reflected there. In all these cases, the maximum fluctuations are less than 1.2%. So this just showed that we can control in this circuit too, with this actual operating, full operating installation, the the current accurately down to very low levels. On the next slide, it's just for the curious example from the same location, measured what the AC signal actually looked like. So nothing surprising there, and almost sinusoidal or sinusoidal kind of signal. It's not exactly sinusoidal. It's not even meant to be exactly sinusoidal, but it's very similar. The two different current steps shown in there, very stable, very nice, even currents. The current stability is shown on the next slide. In this case, again, replicating the same results we got from the early setups, early test installations a few years back. The current stability, currents measured at the substation, at the first fixture, and at the mid circuit from the furthest point of the CCR. And there are again three curves overlapping here, showing that we have the more or less exact same current running through the circuit. So this shows at us that we have the same. So this is measured from the secondary side of the transformer. So this is exactly the current that's flowing through the LED chip. And therefore we know that we have accurate control over the LED, and they will all throughout the circuit, they will have the same luminosity, same even output of light. And what that means on the substation side, if we go to the next slide, because we only put into the field the amount of energy that's needed for the LED to produce the light, we can minimize the energy consumption. So this is comparing the halogen installation before to our retrofitted LED bulb installation run by the Elego CCR. And at the 100% level, the halogen current used in that specific installation was 6.4 amps. The LED current we used was 1.0 amps. The power reduction measured from the input side of the CCR, from the mains network side before the CCR, was more than 91%. And another example calculated there, or measured, not calculated, but shown in the graph is at 10% luminosity level, where the halogen current would have been 4.1 amp. The LED current was 100 milliamps. The reduction in energy usage was more than 96%. Directly, well, there's the fundamental energy difference between halogen and tungsten. That's roughly 1 to 10. So that would give us 10% of improvement, 90% of improvement. The rest comes from the cable losses, from the transformer losses. Because we go low with the current, the energy losses scale in resistive components, as we all know, compared to the square of the current. So the losses really drop to a very, very insignificant level. And thereby we can actually, in the entire circuit, we can exceed the halogen versus LED fundamental energy difference. The rest comes from the cable losses and transformer losses, which is kind of natural. But this can only be realized if we step outside of the actual standard currents. The standard currents are producing sometimes even kilowatts of 1 to 2 kilowatts even of extra losses just in the cabling and the transformers. The 100% luminosity level power consumption dropped from 8.1 kilowatts to 750 watts, and the 10% luminosity level, as an example here, dropped from 2.7 kilowatts to 110 watts. And out of this 110 watts, 70 watts went into the field, and 40 watts remain losses at the CCR. This we can accept. So this we really think is reaching the fundamental efficiency level to be achieved from this kind of a setup, unless somebody comes up with an even better way of producing light than the LED. We really think that we have taken out of the equation all the possible loss mechanisms in a series circuit topology. We're just waiting for the next better LED, so to say, to improve from this. One extra slide, if we go to the next one, still, this is the, but that's not all slide, which was actually produced for the IES specifically during the conference, more or less, from our brand new data from 2 months ago. So this is really measured almost yesterday, so to say. With this technology, having the control over the whole series circuit, it turned out that we can actually ring the AGL circuit like an antenna. So in an open circuit defect or open circuit failure somewhere in the field, it divides the circuit into two halves, and the CCR is somewhere between these two halves. We can use the CCR to ring the circuit and produce enough current into the circuit to illuminate the LED somewhat. And this illumination can be seen by eye, can be measured. This is a measurement from the fixtures showing that the luminosity decreases towards the open circuit failure, which was artificial in this case, in this measurement. But the fixtures right next to the open failure point showed no output at all, and there was no output measured from them. But stepping just a few fixtures away from there started to be a glow, which increased and increased and increased towards the CCR. So this kind of this gives a natural way for the LED bulbs to point the location of an open primary failure in an AGL circuit with just using the CCR in this open circuit failure detection mode. The failure point can be detected visually. And this was something that we had already seen in the lab. We had tested it in the lab, and we're very excited to see how it works in the field. This measurement shows us that it actually works in the field as well. A very nice kind of a bonus feature following from this technology. And all that remains now is our final conclusion slide. This whole research and R&D and development project shows that controlling the LED component directly with the CCR is possible in an AGL installation. The simplestness and robustness of the halogen installations can be replicated with an LED in a similar way, where the CCR directly controls the actual light output from without any engines or drivers in the fixtures, just having a couple of passive components in the bulbs, more or less replicating how the halogen works. These low currents can bring substantial energy savings because there's no need for any extra losses in the fixture or in the cabling or in the transformers. Minimizing the number of components should extend the expected lifetimes of the components. Less failure points, fewer failure points in the field, minimizing the construction of the actual fixture from the electronics point of view. And this also allows us to replicate the halogen bulb dimension, so we can reuse the existing fixtures, the fixture designs, or even the existing fixtures from the field, not throwing away working installations, working fields, just replacing the bulb in them, just as it has been done with the halogen. So what was shown here was a taxiway edge installation, which is probably more or less the easiest kind of from the luminous point of view. But photometrics have already been verified for various fixtures, for example, for runway edge, touchdown zone approach, high intensity approach, threshold. So this is not a low intensity solution. This is a solution for the entire airfield, and we're very eagerly looking into getting verified all possible fixture types and makes and models wherever there's interest. And well, the Elegoo low current solution was on display in the expo. Unfortunately, we don't have an expo today to show you, but we had one at the IES in Detroit this year. So thank you. This will be all from my side at this point. Turning back to Minna.
Thanks, Otto. Well, it was a lot of interesting facts, not only about Elegoo system, but also about AGL in general. You promised me that it takes less than 1 hour.
It did. Slightly.
It did not take 1 hour, but we had some technical challenges at the beginning. I was asking for comments or questions. I actually had one, which I share here. It's about, well, obviously I know something about Elegoo system, and I know that the LED bulbs have been adapted with different halogen fixtures. And it always requires some basic measurements and some basic tests regarding to photometric performance and thermal management. So if there is someone considering to like LED retrofit, what would be your advice to proceed with the project?
First and foremost, be in contact with us. Just getting into contact with us, any one of us, or the AGL at elegoo.fi email address, whichever way you can get in touch with us. We're happy to continue from there. But Elegoo has been developing a process which we're still sort of fine tuning to have this verification done. We need to check a couple of things. We need to check the thermal compliance of the bulb, the fixture, to make sure that the LED bulb is a viable solution or a long-term solution there. And then there's the photometrics. So the photometrics has to be verified. That we will do via an external, a third-party laboratory to keep things independent from the Elegoo judgment. We ran the photometrics tests and see that the solution works. But Elegoo, so far, Elegoo has been making all the retrofit kits, retrofit installation designs, and we're happy to continue doing that. So if you have a fixture, a favorite fixture you'd like to retrofit to LED, just get in contact with us. We'll work it on from there.
All right, and you can start, for example, emailing otto.vainio@elegoo.fi. So I think it's time to wrap up. Thank you for all attending this webinar, and thank you, Otto, for sharing your talk and thoughts. And this and other webinars will be available in Elegoo LinkedIn and YouTube anytime. You can watch them, you can share with your colleagues, you can share in LinkedIn, would be much appreciated. And I guess that's all from our side. So thank you for your time, and see you next time, hopefully soon. Ciao.
Bye. Thanks, Minna.
Thank you.